Right then, tonight then, we're on Met 3. And what we're going to specifically talk about tonight, Mark's going to come on, he's going to talk about frontal systems, how frontal systems work. And that'll lead quite nicely onto lapse rates, about cooling with altitude. And then I'll come back on, because that then leads quite nicely into inversions, and how inversions are develop and how they can affect us. Doesn't matter what you fly, inversions can affect you in a good or bad way. So something to learn tonight. So frontal systems, lapse rates and inversions. You don't see that on the BBC either, do you? People wiping the camera. Right then, so no further delay, I'll put Mark on and we'll crack on with it.
Hi guys, welcome back to Airways Airsports. Thanks again to Andy for starting off. I'm aware we're having a bit of a focusing issue. Not much we can do this end. What I'll try and do is move around a bit and see if autofocus will do its job. Clues in the name, auto. Okay, so what I want to do is kind of pick up from where we were finished on the last Met lectures. We were looking very much at the basics of meteorology and why we have weather in the first place. We also looked quite specifically on this particular chart, which is my favourite chart of all, the synoptic chart. And again, a lot of people just pass this over because in some ways there's so much information on it, it's quite hard to decipher what bit is relevant to us. So hopefully I've been able to break that down further for you so that some of it is a bit more relevant. What we're going to be looking specifically at is this definition of lines that are going on here. Now, on the last lectures we talked about Met, I said to go and download the black and white version and not the colour version, and I still believe that this is the case. There is a little bit more information on the black and white one than on the colour one. The downside being that fronts aren't marked obviously in colour. So what I want to do is just again start really basic when we're talking about frontal systems, and first of all on how to differentiate which is a warm front and which is a cold front. Most of us are aware from an early age from watching the BBC maybe that they've marked it on the map and you've seen the weather girl doing that. But very simple. Let's get started on here. So we're putting that one back up where it was before. When we're looking at a frontal system, we normally see lines of a warm front that are marked in red, and we see what I would call, well, half circles. For me they're like rising suns, so I associate the half circles with the sun, which means they are warm. You have to bear with me on this one. And then we also have a blue line with pyramids or triangles on them. These depict the cold front. Now again, it's in blue, which makes life a lot easier, but when I'm looking at the black and white version, obviously they are black and white. So we still get the same symbols, so the triangles, in my opinion, would hurt, cold, it hurts, varying things there. So they're the ones. Other ones that we also get are what are called occluded fronts. And you'll see these marked with half circles and triangles. And they're normally on a colour chart in purple. So an easy way for us to differentiate the difference between a warm front, a cold front and an occluded front. Now, how do fronts happen in the first place? Why do we get such a drastic change in weather? Why can't it just be one thing or another? Why do we get such a dramatic change when we're dealing with frontal systems? And this again comes back down to the movement of pressure systems within our area. we're going to look specifically at low pressure systems, which we normally associate with bad weather, and this is the reason why, because they are normally the formation of fronts as well. Okay. Now, what you have to bear in mind is when we're discussing meteorology particularly, that it's based on a model. It's if this happens, this should happen, and this should happen. And that's the only thing that we can work on when it comes to meteorology, is what does the model predict. And obviously, you know, there's a lot of experience where you can go, this has happened and therefore this will happen. And that very much is the case. But it only takes a small change in the atmosphere, pretty much anywhere globally, for it to affect the weather somewhere else. You know, we often just look at our own windsock or the hill that we're on and compare that weather. Yes, it can be quite specific to that point, but really we're looking more on a global scale. Now, the reason why we have frontal systems in the first place is all to do with that depression. Now, depressions are low pressure systems, and this means that we have an area of low pressure. Can you see that okay, Barry? And the isobars are really closely packed. What this allows is, it allows for the warmer, more dense air to fall into that void. And as it does, the warm air rushes in behind it. Now, of course, the high pressure wants to equalise the low pressure, the warm air wants to cool down, wants to warm up the cold air, and vice versa. The reason it's called a front is particularly that it's like a battle. There is a battle between the blues and the reds, and each one of them is trying to win. So what's going on really on a global scale for us is we have this low pressure area that's here, and warm air and cold air, and a warmer air. That's pretty much the battle that's going on, the high pressures and the low pressures, and they're rubbing up against each other, and it's a fluctuating line. It may work until it comes across to one of these depressions, and this warm air slowly gets an upper hand.
Sorry Mark, have you turned the autofocus off on your phone?
I haven't turned anything off on my phone.
Mike's doing this.
Still struggling with focusing. What if I come really close and then come really back? Is that working?
It's half and half.
I know, I'm just waiting for it to come through. It's about 5 seconds behind. About 10 seconds.
So what happens is that this then goes in, and now it's got an element of weight because of the more dense air rushing in behind it, until it forms a classic frontal system. This warm air has rushed in to the centre of the low pressure, and the warm air is following behind it. And what also happens is that this instantly sets up a barrier of colder air that is now trying to cool down the warmer air in front of it, setting up 3 depict zones. So we have cool air, warmer air, and cold air. Now, the warm fronts will very much travel in the direction of the wind. Now, we've already discussed about how in the northern hemisphere the wind travels anti-clockwise around a low. So the direction of travel for the front normally is from the west to the east, follows the isobars drawing in around it. Now, this change in pressure also straightens out the isobars. So rather than being a curved line, the isobars tend to flatten off. And what this can do is obviously be a significant change in wind direction. So you see, if the wind is travelling in this direction before the warm front, it's now travelling in this direction at the passage of the warm front, and changing in this direction at the passage of the cold front. So the first noticeable difference is the significant change in wind direction. Now we'll come back to this more on how this slowly overtakes, but what I want to do is bring in that classic warm front and the classic frontal system. There are changes to this, but if you understand the basic and understand on how a classic frontal system operates, then we can add in the variables on a day-to-day basis. So, just for clarity, this is the warm front, and this is the cold front. Okay, where were we so far? How are we doing?
It's better.
Getting better?
It's better.
So this is looking down on plan view. Like I say, if I bring that synoptic chart back in there, you'll see that in the black and white version, obviously the frontal systems that are all travelling here, and here is a classic one there around this depression where that warmer air is, and more dense air has fallen into that low pressure area. Okay, so what we need to do really when we're looking at aviation and how this frontal system is looking at it on a horizontal view, so looking at it this way. So let's put some ground in. So here's our ground. Can you see that okay? Green's not a good colour, unfortunately. And what we have first of all is the warm front and the cold front. Now where you see that on the synoptic chart, that is where it's in contact with the ground. And that's the first important part to remember about synoptic charts. We're having all sorts of tech problems. Okay. So this is where the warm front and the cold front are in contact with the ground. Now, a warm front, because of the density and the pressure and the movement, slow movement of the warm front, sets up quite a shallow angle compared to the cold front, which is quite a steep angle. Now this helps us in somewhat because we have now the easier labels to put on, so we have the cold air, warm air, and the cold air here as well. Now the first things that we should be looking for when looking up and trying to read the clouds is the mark of the start of this warm front. And what you'll see right at the tip of the warm front is the cirrus clouds, like the upper cirrus, the Maris tails, and this is the marking of that pressure as that warmer air is just in contact with the colder air and condensing to form cloud. What we get further on is as this starts to come down, what we need to bear in mind is the lump of air. We have cold air, we have warm air, where these two meet, brings in that dew point, and clouds start to form as the warm air starts to condense. Obviously, as this setting up a nice pressure gradient also encourages the movement of air around that system as well. So what we then find further down here is we get more alto stratus, all marking the warm front barrier. So alto stratus, alto being medium level cloud, stratus, Latin, if Pete the Greek I'm sure is screaming is on there, is flat layer cloud. So this is not obviously the fluffy ones, this is flat stratus cloud. As we start coming down we get more nimbostratus. So this is a lot more defined, but nimbo meaning rain bearing. So this is where we'll start getting our first indications of rainfall as that weight and that pressure is brought down. As we get closer, the warm front gets closer, we'll then get more fractostratus, which I'm unsure if some people know. Fracto meaning broken. So it's still stratus cloud, it's fracto, so it's more broken, it's less defined, and it can bring with it depends if it's rain bearing, but certainly poor visibility as this warm front approaches. What we also might get in this particular area is maybe some small cumulus clouds, CUs, just marking this particular area. So you can see that as that warm front approaches, should our airfield be here, we'd see the cirrus clouds up in the upper higher cloud layers, and we will see this defining layer of cloud getting lower and lower and lower as the warm front approaches. Now, the passage of a warm front can bring obviously some very, very nice flying conditions. Visibility might not be perfect because it's warm air, it can hold more moisture, so visibility might not be perfect. Again, no particular defining cloud layer, but you might find the reciprocals of this being left behind. So there might be, particularly towards the warm front, some upper level clouds. Now, a good way of seeing the marking or the passage of a warm front, I don't know if we saw one the other day. You can look up at the sky, and one side is crystal clear blue, there a cloud in the sky, and then looking over to the other side there is a very defined layer of stratus cloud. It just means that it's broken off about here and it hasn't come down all the way down to the surface. Now, the warm front again bringing us nice areas, but the cold front is moving a lot quicker than the warm front. Significantly faster, so much so that it will overtake that warm front at some point, but this steeper gradient means that we get a lot more defining clouds in a smaller area. A cold front particularly can bring with it some very severe weather, particularly CBs or cumulus nimbus, or Columbus nimbus as I once called them 10 years ago. So CBs, if you ever see CBs on a weather or aviation forecast, probably not a good day to go flying. And these are the very defined, flat, large bottoms and anvil shaped off in the way. Anvil's probably the wrong direction. But you can see that the cold front is going all the way through it. And of course these are severe, severe thunderstorms, yeah, very stormy conditions. But only in a very short area. At the passage of a cold front, we then might get some larger cunims that might bring with it some short showers, but visibility is going to be very, very good. And again, once the cold front has passed through, probably not such a bad flying day or a flying hour to go. Now, how quickly do these move? Well, again, it's not given to us as a secret. On one of the forms that I've shown you before, you'll see this is the 215, and you'll see here in this zone there we have all of these bubbles, but if you see in zone B you can see the cold front and the warm front being marked in. Now this isn't a classic model, I appreciate that, but you'll see that. But what you'll also see, or should normally see, nothing showing. You'll see an arrow with a speed in knots, and this isn't the wind speed, this is the speed of the zone or the fronts. And so we might get a speed of maybe 20 knots, so that we know that this warm front is travelling at 20 knots. Very, very simple. So if we are here 40 knots away, it's going to be with us in 2 hours. It's very, very, very simple. So how far away is this? Well, if we're looking at the classic model, this can be up to 500 miles. Which means that if we're looking at these cirrus clouds, we can work out that that warm front is going to be with us in about 2 days or so. This is why you'll particularly get farmers, or certainly the old meteorology guys, looking up at the clouds and go, it's going to rain. Or another tip, if you ever see the farmers muck spreading, it's going to rain. A few local tips. Whereas the cold front is only around 50 nautical miles from start to finish. And so it's a very quick moving, and this will be travelling significantly faster. And what happens with this is then that cold front will eventually catch up with the warm front and set up a situation which is called an occlusion. Now, an occlusion is probably the worst type of front that we can have. So if I bring this in here now on a normal scale, here is our low pressure. Here's our warm front. Here is the cold front. Change in the lines, and as this cold air, this cold front catches up with the warm front, it starts to force that warmer air up and out of the depression, and this sets up the occlusion. And occluded fronts are particularly bad because they retain all of the bad weather from a cold front and all of the bad weather from a warm front, all in a specific area. And it's a bit like zipping up. So if you can imagine that this is the zip and the cold air is just trying to zip up that frontal system and force that warmer, more dense area out of the scenario. So occluded fronts can be quite vicious. So I'd say they're normally marked with either in purple if you're looking at it on a colour chart, or they'll show both symbols of the cold and warm front together. If I can show you an example of that. So on the black and white version, you can see this one there is an occluded front, that one there, you see. Now, coming back on this, on where does this sort of come into play from a classic model in a comparison to what goes on in the real world? Well, of course, what goes on in the real world is that it wants to do this, but sometimes you see the triangles as showing the direction of movement and the sun, so they are chasing each other. That's quite a big area here for this. They're going in opposing directions. If we were looking for a classic warm front or frontal system, it would look like this one here, where the cold front and the warm front are in the same direction, and you can see where it's occluded and zipping up that area there. So warm fronts and cold fronts, it's very important that we do understand what these symbols mean on a synoptic chart, and more importantly, what type of weather are we going to get. And it's worth, particularly if you're studying for an exam, obviously we don't tell people on how to pass their exams. What's the point in that? What we can do is give you information so that you can understand the topic, and then the exam's easy. So it would be worth, particularly in things like the Cosgrove book or any meteorology book, study what the weather would be like here, here and there, because there are three definitive different types of weather. One is going to be lowering cloud, poor visibility out to the west because of the direction of travel, possibly rain bearing at the passage of the front. As a passage of the front, we might get poor visibility in the more warmer dense air, significant thunderstorms at the passage of a cold front, and then in the colder air we get more dense, colder air. I may have been saying that wrong for the entire lesson, bear with me. Cold air is more dense, warm air is less dense, just in case I got that wrong somewhere. So the more dense air, holding less moisture, you're going to get a lot nicer conditions, certainly not going to be too many thermals around. So the passage of a cold front can bring with it obviously some nice flying weather in what would normally be a depression. Okay, so that's frontal systems. I don't want to go into too much, or could spend hours talking about frontal systems. But what I do want to do is come on and talk a little bit more now about lapse rates, because this is something else that a lot of people really get confused about, and I don't want to go into the full realms of lapse rates. I just want to try and make it a little bit more self-explanatory. Okay. Have our focusing issues sorted themselves out?
Keep moving backwards and
Is
forwards.
it me moving backwards and forwards? I'm trying to make it work for a living. Okay, so in order to understand lapse rates, we need to bear in mind that there are a number of lapse rates. First one being the ISA, so we talked about the International Standard Atmosphere. So the ISA states that for every 1,000 feet, the air temperature will cool by 1.98 degrees C. That's what they say. Never really the case. Certainly we would round it up to 2. Unless you got a question on it in your exam, then it definitely is 1.98. Another lapse rate that we can get is what's called the ELR. Any guesses for ELR? Environmental lapse rate. And this is the important one because this is what it's actually doing. So the ELR is what it's actually doing. This is where they send the weather balloon up, recording temperatures and report it back to us. So the ELR is whatever it is. We also get a dry adiabatic lapse rate. Now, this is where a lot of people can get confused, and this is the DALR. And again, this is working on the model because the dry adiabatic lapse rate isn't so much that it's actually dry air, it just hasn't lost its moisture yet. So it's still retaining moisture, it hasn't turned into water vapour. And we know that this air will cool by 3 degrees for every 1,000 feet. Quite a significant number to remember, certainly on some of those thermic days. And then we also have the SALR, which is the saturated adiabatic lapse rate. And this is where it's met dew point and it's now released that moisture into the atmosphere, and normally the formation of clouds has begun. And the saturated adiabatic lapse rate, it cools at a 1.5 degrees C per 1,000 feet. So when we're talking about lapse rate, it's very important that we're aware of the 4 that are there. Now, this one, or these two, only come into place when we have air that has been forced to rise. And there are a number of ways in which the air can be forced to rise, adiabatically, katabatic, thermic convection, and the list is endless. So let's try and bring this into a realistic model on where we might see these. So, first of all, we're going to put on a basic scale. And some new pans. And we have 1,000 feet, 2,000 feet, 3,000 feet, 4,000 feet, 5,000 feet and 6,000 feet. So that 1,000 feet, I just saved me writing a load of zeros. Now, the ISA says that the average ground temperature is 15 degrees. And it says that for every 1,000 feet it cools by 2 degrees. So 13, 11, 9, 7, 5, 3. So that's what the ISA says it should be doing. Now, the ELR, the environmental lapse rate, is what it's actually doing. And we touched on this briefly before on the form 214. So look at that a bit closer. And you'll see on this end box here, or any of the end boxes, there is a scale here with a degrees in Celsius for at what it actually is at the actual altitude it's saying. And whatever it actually is, that's what the ELR is. It's working that out for us. So let's give us a ELR, let's say it is 15 degrees. Let's say that this is 12, 9, 7, 5, 3, 1. So you can see that although we have the same surface temperature, that the air temperature here has cooled by 3 degrees. And here 9 to 12 is 3 degrees, then 2 degrees, then 2 degrees, 2 degrees, and 2 degrees. So the first 2,000 feet, the air is cooling at 3 degrees. That's what the ELR is. As opposed to above 2,000 feet, where it's cooling at 2 degrees. Now I'll come back to the ELR in a moment, once we've talked about the DLAR and the SLAR. Because when we're talking about the air that's being forced to rise, there must have been a reason for it to change. So the easiest one to look at is thermic convection. The ground has been warmed up slightly. It could be a patch of tarmac, it could be a hangar roof, it could be a field of crops. Anything that would allow that particular area to slightly rise, and it only needs to be a little bit warmer than the surrounding air for it to rise. Hot air rises, very, very simple. So let's say it's changed by ½ a degree, and so the surface temperature is 15.5 degrees C at the surface. It is warmer than the air surrounding it. So this is where it then follows the DLAR, adiabatic lapse rate of 3 degrees C per 1,000 feet. And so the temperature here would then be, I'll make sure we got these right, 12.5 degrees C, 9.5 degrees C, 6.5 degrees C, 5 degrees C, 3.5 degrees C, and 2 degrees, 22 degrees C. So in this scenario, this ground has warmed up more than the surrounding air, and that hot air has been given out like a bubble and being forced to rise. So this bubble then starts to rise, and you can see the difference between here and here is 3 degrees. Then as that bubble continues to rise, it still begins to cool, and is still cooling at 3 degrees. Now let's throw in dew point. Now dew point is the temperature at which that air mass can no longer hold any more water vapor, humidity. Humidity reaches 100%, and so it can't go anywhere. It now condenses into cloud. So let's say that the dew point on this particular day is 6.5 degrees C. There we go. So now we have the formation of cloud. Turning this dry adiabatic lapse rate into the saturated. It's given out all of its moisture. So this will then cool at the saturated adiabatic lapse rate of 1.5 degrees C. And you can see here it's still rising, but it's now cooling at 1.5 degrees C. 1.5 degrees C. 1.5 degrees C. And so this is the difference between the dry adiabatic lapse rate and the saturated adiabatic lapse rate. There must have been a reason for it to rise in the first place, and when it does follow the classic model. These figures are really, really useful then when we are comparing them to the ELR, the environmental lapse rate, because using the base model that hot air rising will cool at 3 degrees means that we can look at something like a 214 and work out if it's going to be bumpy, if the air mass is going to be stable or unstable. So an air mass that is being forced to rise, well, what is it? Is it stable or is it unstable? It's unstable, yeah? So we can see here, coming back to our ELR, which is what it's actually doing, that the air is rising at 3 degrees. Now here's a tip, that if the ELR, I'm going to bring this in, if the ELR is the same or greater than the DLAR, then we are in a unstable air mass. The air is rising. So in this, at 1,000 feet, we are unstable. It's still rising air, so at 2,000 feet, 3 degrees lapse rate, still rising air. It is unstable. But then you can see at 3,000 feet, it's now rising at 2 degrees. It's less than the DLAR, meaning that we have stable air mass. And again, 4,000 feet stable, so we can see that the air is rising up to about 2,000 feet when it then starts to calm down. So again, depending on what it is that you're flying, you will look at the ELR and make a decision on what altitude you want to fly at. Particularly for me, when I was a flex wing pilot, I already discussed this, the thought of me flying in any hint of a thermic day, I would put my aircraft away. I didn't like it scared me, again, until I met Andy, who threatened me and set me up. But from this, I could work out that actually if I take off and climb above 2,000 feet, that the air is going to be more stable. So let's look again back at our depiction here on the weather that we're using. We can see I'll write it down. So this is the weather from the chart that I downloaded the other week. At 1,000 feet, it is plus 0.9. At 2,000 feet, it is plus 0.5. The next jump is 5,000 feet, where it is plus 0.3. Have I got no, I haven't got it. Let's assume, based on this, that the air temperature here is going to be, the surface temperature is 12 degrees. So between 12 and 9 we have a 3 degrees. It's going to be unstable. Between 1,000 and 2,000 we have 4 degrees. The lapse rate of 4 degrees. Barry's got his hands in the air at the thought of a 4-degree lapse rate. I personally aren't even thinking about flying anywhere around 2,000 feet. But you can see that between 2,000 feet and 5,000 feet there is only a temperature change of 2 degrees. So above 2,000 feet, if you don't want to be bounced around in thermic, lumpy, unstable air, is the zone for us to fly. And again, this is where you're going to find all those paraglider pilots, and this is where you're going to find a lot more GA fixed-wing aircraft, if you understand the reports that you're being given. Okay, I haven't really left Andy much time, so I'll very much rush on. I hope that this has explained a little bit more in detail, probably went a bit more detail than I wished, on lapse rates. Again, if you have any questions on this, please feel free to message us and we'll try our hardest to answer. But I'm going to hand back over to Andy, who's going to talk to you about inversions. Again, bringing this into play, but I'll let Andy explain that one away for you. Thanks again for watching, guys.
So, inversions. So it throws this a bit out of the window. Somebody asked, what is a lapse rate? It's the change of temperature, within an atmosphere. And it doesn't mean that the temperature necessarily has to go down with height. It goes down with height because the sun heats the planet and the planet radiates the heat into the atmosphere. And as we go up, the pressure drops, which also, when you decrease pressure within the gas, that also decreases the temperature. Now, if we increase the pressure within a gas, that increases the temperature as well. So if we pressurise a gas, it makes it warmer. So there's different forms and there's different ways that inversions can develop. And an inversion is basically a pocket or a layer of pressurised gas within the atmosphere, or layers of pressurised gas within the atmosphere. There's different ways that can be formed. We will look at the way that high pressure, Mark spoke about high pressures the other night, and the high pressure is a body of air that is turning and falling and pushing against the planet. Yeah, this creates a very stable atmosphere. As it falls and pushes down, things get more stable and it starts crushing the air below it. Overnight, the sun obviously isn't out and the planet cools, and that cools the pocket of air next to the Earth. As that pocket of air cools, it becomes denser. The air pushing down on top of it, then starts being crushed against this cool layer of air. As it's crushed, it warms up, and this creates an inversion. So this is your classic inversion. Here's the ground, and you've got a body of falling air, you've got cool air next to the ground, and that air is crushed on top of it. And this is during a period of high pressure. How do we know there's an inversion? We can usually see it from the ground. When we look out from the horizon, we'll see a brown layer. This is usually an inversion, a sign that an inversion is there. So what? How does that affect us? That we have this layer here of crushed air that is warmer. So it throws the lapse rate a bit out. So here we would have a normal lapse rate. Let's say the inversion's 1,000 feet up and we've got 3 degrees of cooling. Then all of a sudden it gets warmer, and then it starts to cool again. A few things can happen over time. You'll see a forecast, and you've got a forecast for a day, and you think, well, great forecast, I can go out in my paramotor, go out in my microlight, I've got a 3-4 mile an hour wind that's going to blow. And you get there to your site to go and fly, and it's really windy. You think, well, it shouldn't be. What's happened? The day before, it's been quite breezy, an inversion's formed overnight, and it's actually trapped the wind under the inversion. So where you would normally have this layer of air in this much, it's all been pushed down now, like it's going down a tunnel, like a Venturi effect. So you've got a strong wind. If that inversion warms out during the day, as the sun heats everything up, it starts warming out and breaking that inversion down, the wind may go away, because as the inversion lifts and goes away, the wind will drop. The same can be said, you don't expect to go flying, you go out to your field and it's not windy. Because the air, the strong wind, is trapped over the top of the inversion. This might catch you out. You take off, you think, well, happy days, it's a nice breeze, you go off. Normally you will know you have entered into an inversion. The first sign is probably it will get a bit bumpy. You've got a layer of crushed warm area that's mixing itself around, and it will get a bit bumpy. The next thing is you will hit the stronger wind that's going over the top, and all of a sudden, if you fly into the wind, you'll start flying backwards, or you'll stop, your ground speed will stop, and you'll go, well, it just got windy. But it'll probably get smooth. How else can an inversion catch you out? You take off, it's nice and smooth, you go up through the bumpy bit of the inversion, and you get into the upper air is not strong, it's good, you're all happy, you're up there 2-3 hours, you come back down, and all of a sudden it gets as rough as hell. And the reason being is the sun's on the ground, things are starting to get thermic. thermals are happening. But what happens is, these thermals and all this convection that's happening low down here, is hitting the inversion, and it can't get through. It will bounce off. Explosive sound waves will bounce off an inversion. There is a case of during a nuclear test in Russia, I think it was, that they let a bomb off, and the blast actually killed 3 people that were a long way away, because the blast was actually trapped under the inversion layer and travelled further in a lower wave. It actually destroyed a building and killed some people. So inversions can be incredibly powerful, and a thermal can't get through them. Or a thermal can get through them, but very slowly. So where you might have a very fast climb rate up to the inversion, if it can get through it, your climb rate will become very slow through the inversion. And my advice is, if you are climbing through an inversion, keep with it and just work it and work it and work it. And hopefully when you pop out, the acceleration will happen again, the thermal will be allowed to rise quickly again. So if you can climb through a inversion, if you're in lift in an inversion, then stay with it, because it ain't going to get any better. It'll only get worse. So just stick with whatever lift you've got. I've had a case where I've been aero towing, hit an inversion and just in the tug, and just could not climb, just kept bouncing off the inversion. I just could not climb through the inversion. I've also occasions, once you enter the inversion, visibility becomes extremely poor. This is another thing that can catch you out, especially if you're flying and your flight plan is towards the sun. It is literally, can be like flying into a cloud. It is white out. Boom. Your visibility is absolutely terrible. You look to the side away from the sun, you can see. You look ahead of you, you can't see a thing. You can't see down and around. You end up having to S along. The safest route is to S along, so you can actually see. Cuts down the chance of a mid-air collision. So I've been temporarily unaware of my location on one occasion because of an inversion flying back in the evening towards the east, and I couldn't get above the inversion, I couldn't fly below the inversion. I was in the inversion, and visibility is really poor. How else can an inversion catch you out? What happens is, over time, you've got all this energy building up under this inversion. An inversion during a high pressure can last for days and build up, and you can have inversions building on top of other inversions. So you've got inversion on top of inversions. What an inversion then needs is something to break it up. If it can't warm out from the sun, it needs something to break it up. If that inversion is hit by a small cold front that contains a lot of moisture, and moisture contains a lot of energy, the inversion can break very quickly. This is where you get your Q-nim build, or you get rapid instability within the atmosphere. You've got all this energy that's built up over days. You've got a lot of moisture in this energy as well that wants to escape. You pop a hole through this inversion, it's a bit like if you took a bottle of pop and just opened it, bottle of tonic water, and went shh, like that, opened it, fine. If you take it, and you shake it up, give it a good shake, then pop it, or you shake that champagne and pop it, you're popping the cork, you're letting all that energy out in one go. So you get all this energy rushing through this gap. You get all that moisture starting to expand very quickly. You hit this one, bang a hole through your second inversion, and all of a sudden, where you normally won't get any sort of convection working over 36,000 feet, it will work right out into the atmosphere, right into the upper atmosphere. And that's when you'll get your Q-nim and things start to go bang. If you're in the air during the inversion and you start seeing towering clouds, where it's been very blue, so you start to see clouds that are cumulus but towering, yeah, what I would call marging. That's the official name for them, marging, because they look like Marge Simpson's hairdo. So when you see Marge Simpson's hairdo in the sky and you're popping along on your paramotor or you're flying along, yeah, in your microlight, might be a good time to consider how quickly you can get out of the air and back on the ground, because that is about to explode. That is a sure sign that the atmosphere has become very unstable from there to there, and it will soon go to there very quickly. So marging is a sure sign, and that's the many ways that inversions can catch you out. Release of energy, visibility. The good thing is they can keep upper winds high, but then you get a lot of convection below them that's bouncing around underneath them that can't escape where it should go to, so it can become very rough down low. So study inversions. They're hard to predict. You don't see inversions on weather forecasts. The easiest way to see an inversion is look out of your window, look at the horizon, tell you what the horizon is telling you. What's going to be very interesting in the coming months, with the amount of pollution we've cut out of the atmosphere at the moment, is how well we will see inversions. Inversions are brown because they're holding pollutants. They're holding the carbon monoxide from exhaust pipes, from factories. So it'll be very interesting to see how defined inversions are in a month's time, when there's been a lot less pollutants in the atmosphere. Will we see them as defined? Because they will be there, but it's whether we can see them as defined. That's about it on inversions. If you want to know any more, please ask some questions on inversions, and I'll gladly ask them. But something that can work for you, but can very much work against you as well. I think that's about it for tonight. Thank you for Barry for being our cameraman. I know we've had a focusing issue, we don't know why, tonight. We have now got a GoPro 7 here, we just couldn't set it up in time, so hopefully it'll be better. Sunday night, 7 o'clock, we've got Will coming on, talking about a few different things, tips and tricks from somebody who's an instructor and also a commercial pilot, who can talk to you about different tips and tricks and how to make things easier for yourself in the air. Yeah.
If there's anyone out there who knows how to get the code for the GoPro 7, the password out of it, let us know.
Yeah, if anyone knows how to get, Barry's got the GoPro 7, it's not a new one, and we need the code so we can connect it to an iPad or an iPhone to the Wi-Fi. So we need to know how to get a code out of a GoPro 7. Yeah, so all you dodgy hackers out there, that I know there's some here because I recognise the names, please do tell us how we might be able to do that. That would be absolutely fantastic. But until Sunday, when Will's on, remember, stay safe, stay well, and stay at home.